Okay, now that we know about the pH scale, let's look at finding the concentration of H plus or H3O plus and finding the pH of acidic solutions, acid solutions. Well, recall we have two types of acids, our strong acids, which dissociate 100%, and our weak acids, which do not dissociate 100%. Good news is the strong acids are fairly easy to do because if you have a strong acid dissociates 100%, that means if you had zero point 0.1 molar HCl and it's dissociated 100%, that means our concentration of H plus is 0.1 molar and our concentration of chloride is also zero point 0.1 molar. Truth is, we don't worry about the concentration of chloride too much because it's the concentration of H plus we need to know to get pH. So there's the deal. Whatever the concentration of your strong acid is, if your strong acid is 0.5 molar, then the concentration of H plus is 0.5 molar because it's dissociated 100%. So we go back to this problem. If you have 0.1 molar HCl, what's the concentration of H plus? 0.1 molar. What's the pH? Well, pH is negative log of that 0.1 molar. pH is 1.00. So that's a nice, easy problem with strong acids. Just get the concentration of the strong acid, that is the concentration of H plus. Take the negative log of that concentration, you have the pH. Things get a lot more fun, however, if we're dealing with weak acids, because weak acids do not dissociate 100%. Weak acids are at equilibrium, therefore we're going to need ice tables to figure out the pHs of weak acid solutions. So here we go. If concentration of CH3COOH, acetic acid, note that acetic acid is also can be written as HC2H3O2. That's another way to write acetic acid. You might see it that way. Lots of people like to write it this way in general chemistry to note that this is the hydrogen that goes away. In organic chemistry, we tend to write it this way. Recall it's a carboxylic acid, and it's this hydrogen out here that goes away when it dissociates. All right, but if the concentration of acetic acid is 0.1 molar, the H plus concentration is not going to be 0.1 molar because it doesn't dissociate 100%. So what is H plus concentration? We need an ice table, and recall with an ice table, if you need concentrations at equilibrium, you need to know the Ka, and you can find the Ka in various tables of Ka values. For acetic acid, it's 1.8 times 10 to the minus 5. All right, so to do this problem, we know that acetic acid, if you put in water, dissociates into H plus H3COO minus. Initial change, equilibrium, the initial concentration of acetic acid, 0.1 molar from the problem, and before it dissociates, we don't have any of these two guys. The change will be minus x, because since we have 0 here, we know that this has to move to the right from this point, from the beginning point, to get some of these guys to create equilibrium. So then the equilibrium is 0.10 minus x, and x. Here is our equilibrium constant expression, Ka, since it's an acid dissociation. Ka equals H plus times concentration of CH3CO minus times CH3COOH. 1.8 times 10 to the minus 5, given in the problem, equals x squared, since this is x and this is x, over 0.10 minus x, our equilibrium value for CH3COOH. And question, do we need to do a quadratic, or can we take the shortcut? Which of these can we do? This is 0.1. This number here, the Ka, is less than 1 times 10 to the minus 4th. We can very assuredly take the shortcut, ignore the minus x, and just solve for this x up here. And here we go, 1.8 times 10 to the minus 5th equals x squared over 0.10. Do some math. We find the concentration of H plus is 1.34 times 10 to the minus 3rd molar. And then we find that the pH, take the negative log of that, is 2.87. Note that Ka's normally have 2 significant figures. So your pH will normally have 2 significant figures, 2 numbers after the decimal place. And so here it is. 0.1 molar acetic acid has a pH of 2.87. Recall 0.1 molar Hydrochloric acid has a pH of 1. Strong acids dissociate 100%, means a lower pH value, a more acidic solution. And also remember, pH is a logarithmic scale. It is a factor of 10 scale. So a pH of 1 means it is 10 times more acidic than a pH of 2. And this is 2.87, close to 3, which means this solution here of HCl, pH 1, is almost 100 times more acidic than this pH of 3 solution acetic acid, because it's 10 to go from pH of 1 to pH 2 dilutes by a factor of 10. 2 to 3 is another dilution by a factor of 10. 10 times 10 is 100. So, ice tables to figure this out. Good stuff there, but if you really love ice tables and you're good at them, then you should have no problem. So, let's see if you have a problem. What is a pH of 2.0 molar HClO? Note the Ka for HClO is 2.9 times 10 to the minus 8th. So if you want, pause the video at this point, work out this problem, and when you restart it, we will go through the problem, because I'm going to go through this problem right now. Okay, here we go. So we've got 0.2 molar HClO. First question, is it a strong acid or a weak acid? Well, it's a weak acid. How do you know it's a weak acid? Because it's not one of the 6 strong ones we memorized. Well, what are the 6 strong ones we memorized? Oh, that's right. HCl, HBr, HI, H2SO4, HNO3, HClO4. And this no 4 down here is HClO. So this must be a weak acid. Therefore, we realize we're going to have to use ice tables. Of course, we were given a Ka value, so we knew we were dealing with a weak acid also. So then ice tables to figure out the concentration. Well, I hate writing everything out, so I'm just going to use HA as my ClO. HClO will be in equilibrium with H plus A minus. Initial, change, equilibrium. I like to draw my line right now. All right, what's our initial concentration of HA? 0.20 molar. How much H plus do we have before any dissociation? 0. And 0A minus before dissociation. All right, the change. How much of HA is going to dissociate? I don't know. Minus X. How much H plus comes into existence? Plus X. And A minus is also plus X, because our stoichiometry is 1 to 1 to 1. All right, so at equilibrium is 0.20 minus X, X, and X. Okay, so far so good. What do we do with this? Well, we know that Ka is going to be our concentration of H plus times our concentration of H plus concentration of A minus divided by our concentration of HA. And we've got values now for Ka is 2.9 times 10 to the negative 8th equals our concentration of H plus is X, concentration of A minus is X, divided by 0.20 minus X. Hopefully we can see X times X. This is going to be X squared. Well, the question is, can we ignore this minus X? Because we're going to quadratic land if we can't, but, oh, yeah, this is 10 to the minus 8th, 0.2. Sure, we can ignore this minus X. So moving all this up here, we get 2.9 times 10 to the minus 8th equals X squared over 0.20. Working out a little math, you should multiply 0.2 by 0.2 and square root. You should get that X equals 7.6 times 10 to the minus 5. Recall, X is our concentration of H plus. Therefore, our concentration of H plus equals 7.6 times 10 to the minus 5th molar. pH is the negative log of the concentration of H plus, so it's a negative log of 7.6 times 10 to the minus 5th molar. pH equals 4.12. Note, 2 sig figs, 7.6, 2 after the decimal place, 0.12. And so, yes, pH of 4.12, it is acidic since the pH is less than 7, but it's not very strongly acidic. Okay. Last thing for this video is the concept of percent ionization. That is just a term where you can calculate the concentration of your ionized acid divided by the initial concentration of your ionized. It's essentially the concentration of H plus divided by the initial concentration times 100%. So note, our concentration of H plus here was 7.6 times 10 to the minus 5th molar. That goes at the top, concentration of ionized acid. Our initial concentration was 0.2 molar, so 7.6 times 10 to the minus 5th divided by 0.2 times 100% means our percent ionization is 0.038%, which means when this reaction happens, when you put HClO into water, very, very little of it dissociates. Only 0.038% of it actually will dissociate. The vast majority of the HClO stays as HClO. Very, very little dissociates into H plus and A minus. All right, so that's enough for this video. We'll pick it up next video when we start mixing weak acids with strong acids and seeing what happens.